Hello and welcome to the Environmental Test and Design webinar, Good Vibrations, MIL Standard 810G, Shake and Shock Requirements for Military Equipment. My name is Belinda Stashkevich and I'm the editor of Environmental Test and Design. Environmental Test and Design, which launched in 2009, specializes in the interrelationship between electronic systems and devices and their environments. This webinar is presented by Steve Ferguson, Executive Vice President of Washington Laboratories. Steve Ferguson has worked in the compliance test arena for over 35 years at test labs and manufacturing companies, designing products, developing procedures, and performing tests. He presents various courses on EMI and EMC compliance. He's an INARTE certified EMC engineer and administers the INARTE-approved Washington Laboratories Testing Center. This webinar will be interactive. You will be able to ask questions and answer polls, and we encourage you to participate. Take a look at the GoToWebinar navigation pane. If at any time you have a question, we ask you to fill out the type box and hit send. To make this screen minimize and maximize, click the arrow button. To raise your hand to ask a question or to report an issue, click the hand icon. We will present the topic for 45 minutes, followed by a 15-minute question and answer session. Before we begin, we have a poll question for our audience. Attendees, please answer the following question. Do products more frequently experience shock or vibration issues associated with electrical circuit operation, structural integrity, retention of attached parts, or other? We'll give you a few seconds to answer this question. We're getting some results in. Looks like there's a division. And we're kind of split between the first three. Steve, over to you.
Well, hello, I'm Steve Ferguson. Thanks for your input. This is one of the poll questions that I don't have an answer. I was just kind of looking to see if what the people experienced. These things are typical, pretty typical, and I didn't know if there was something that was dominant or not. So I'm using this audience to kind of get some information. So the split says it's all these things come into being apparently. And there are other things that could pop up, like one time during vibration we had the unit burn on the table. So it can be quite dramatic at times. With that, shall we get started? There's a real focus on shock and vibration associated with this MIL standard testing. 13 of the 29 test methods documented in MIL Standard 810 evaluate dynamic susceptibility. The list is pretty extensive here with some things feeding on others. Acceleration, and acceleration can be not only like a shock acceleration where you get an event, but also a continuous stress. Vibration, acoustic noise, regular dynamic shock, power shock, gunfire vibration, which is kind of a shock test with vibration affiliated with it. And one of our standby, the method 520, the temperature, humidity, vibration, and altitude. Now a lot of people look at this and decide that they're doing all four things at once. Seldom is that the case, because if you have an extreme altitude, you don't have humidity. You don't typically have high temperatures unless you're in another environment that's also at altitude. But generally speaking, 2 or 3 of these things get combined, and seldom all of them. There's ballistic shock, vibroacoustic temperature things, time waveform replication, which really takes the events of a recorded waveform and applies that to the shock evaluation criteria. Rail impact, multi-exciter, which now the shock and vibration happens with multiple events happening simultaneously, typically associated with large articles where you end up with different stresses at different points on the item. Mechanical vibration for shipboard equipment, those unique things associated with shipboard get evaluated. So as you can tell, there's a real focus out of the standard for doing these kind of evaluations. It's a big exposure event, and we need to examine these things pretty critically. Our focus, we're going to deal with 514.6, the vibration, and 516.6, the shock. I picked these 2 methods simply because they're commonly done. A lot of tests come into being using these things with possibly other things supporting them, like the multi-exciter, the time waveform, and other events. There's a lot of varieties in these tests, lots of methods, categories, etc. COTS procurements, commercial off the shelf is what COTS means. COTS procurements usually call out these things because we don't know where the environment is. It's built for a lot of environments. They don't really have a life cycle plan because they don't have a full deployment known. It's not like it's building something just to go on a truck or just to go on an airplane. It's being widespread applications of common hardware. And with that, there's no life cycle plan associated with procurement. So we don't have a lot of analysis and things of that nature supporting the purchase. There's also a big effort to satisfy sales without a specified purchase. Some people are trying to say, well, let me just qualify the product for anything and everything. So this is a pretty typical thing going on. In 514.6, the procedures, there's a purpose, and it's to assess the performance and life cycle of vibration exposure. The development testing typical is integral to the design strategies. So we look at the development process to figure out what we're trying to do. There's a reliability program where we assess the effects and deterioration, something that happens over a long period of time, or to assess deterioration with continued exposure. And the qualification program is to demonstrate the operation and survivability, depending on which one you're targeting, at any given point. So these are where the life cycle plan really comes into being to say, I need to qualify the product so I have some sort of assurance that during life it will operate in an acceptable degree of performance. There's 4 basic procedures going on. The general vibration is used for materials to be transported as secured cargo or deployed for use on vehicles, including fixed and rotary wing aircraft. Loose cargo transportation, used for material to be carried in or on trucks, trailers, or tracked vehicles. Typically, the loose cargo is not associated with an aircraft because it's never loose, it's always restrained. Large assembly transportation, used for large assemblies installed or transported by wheel-to-track vehicles. These things could range anywhere from other vehicles being transported by rail or by other vehicles to you name it, kind of transportation. It's typically secured or strapped in place or tied in some manner. There's assembled aircraft store, captive carriage, and free flight. It's used for aircraft carriage, free flight portions of aircraft stores, and free flight phases of ground or sea-launched missiles. Remember, aircraft stores are things attached to or installed in an aircraft, not permanently there. Maybe a container is brought into the aircraft and it is operated during the flight, like a command or a communications center that gets installed in an aircraft for deployments. So in all this process, what applies to fixed installations? Nothing. There's no real fixed installation vibe or shock testing associated with the MIL standard 810G. But yet we see this all the time to fixed applications because there are real fixed applications. And sometimes it just simply falls down to general integrity and etc. So we don't really have a profile. We don't know what the exposure is. We don't know what needs to happen. So for fixed facilities, these things really need some definition. The life phases, we have some 4 life phases associated with 25 categories to define those life phases. For the manufacturing and maintenance function of the life phase, there's 3 categories involved. From the manufacturing, where subassemblies, pieces are built, component handling, that involves bending, folding, riveting, and things of that nature, where it's integral to get the system built and through the manufacturing process. I want to highlight something in here that's frequently omitted, a piece of metal. We're designing a product that has a highly permeable metal to take care of magnetic field as shielding. Little is it known that sometimes these things are exposed to shock and damages like bending, bending breaks, hammer, folding, etc. And those shock events that happen to that metal realign the atomic structure of the atom, so the shielding or the magnetic properties are no longer where they used to be. So part of the evaluation would be expose that metal to the shock and see that it still performs in the manner that we expect it during the events. This testing needs to be done on an atom that has went through shock and vibration and then through the shielding effectiveness portion of it to see that it retains its life. And remember, this happens over and over again, so things that are shocked frequently are going to deteriorate much more rapidly. There's shipping and handling within the facility, the test and the burn-in. Any transportation happens prior to packaging, where it goes over to another building for shipping and packaging. Environmental stress screening gets involved in this manufacturing thing, where the exposure, duration, and the number of cycles affect things during the process. This may include tests other than vibration. There's life phases associated with transportation or the material's cargo. Remember, Appendix C in the mill standard provides several of the profiles here. There's category 4, 5, and 6 where trucks use secured cargo, loose cargo, and large assembly. Category 7, 8, and 9 are for aircraft with some particulars on jet, propeller, helicopter. We also have marine vehicles and trains associated in those categories. Category 10 really pulls in marine vehicles, and the category 11 are the train systems. The life phase category 12, 13, and 14 are for aircraft for installed material. 15, 16, 17, and 18 are aircraft stores. Those assembled stores and installed in stores both. Things that are carried, not necessarily permanently fixed in the airplane. Category 19 is a tactical missile, 20 ground equipment installed in tracked and wheel vehicles. It's the most common item for things that get deployments. 20 is called out more than most. 21, I suspect near shipyards and the like, we see more of category 21. 22 are engines, particularly on turbines, material installed in them. And category 23 is for personnel carry, so it's an operational aspect of the life phase. Then there's a supplemental life phase where Appendix E defines some of the profiles. And then here we have this category 24 for all, the minimum integrity. So things installed on isolators or an undefined life cycle. Does not alleviate the need for transportation qualification. So those tests before for transportation do not get overshadowed by this category 24. And there's category 25 for all vehicles that have external cantilevered, antenna, airfoils, wings, and things of that nature, masts that have a momentum associated with them, the fulcrum event where other stresses apply to things and cause these items. If anybody's ever watched an antenna on an automobile, a radio antenna, it's vertical, and you can see at certain speeds you'll get a vibration and oscillation where the thing is rippling, like a tuning fork. You can actually see the movement at a resonant place. All the wind directions and things cause that. I've got an example here of a test. I'd like to see if we can play this thing. Oh, another poll question.
Thanks, Steve. Did it pass? Yes, no, need functional test results, or can't tell? Okay, a few more seconds. And we apologize for the video. It's a little bit slower than we would prefer. But when we have our website, we'll have the presentation on there and everybody can watch it. It should be a little bit better. And results, and back to you, Steve.
Well, what did the results say there, Belinda? Did you get a kind of a thing going on? Didn't hear back. The idea is that it would typically be considered it did not pass. The thing came apart. It had pieces fall out of it and land on the floor, so generally that's not acceptable. But it could be a development test that says I need to determine how I need to fix it. So we went in with a base position to determine the requirements. So without knowing some of the elements, you really can't tell whether it passed or failed. In that case, this was a second test of that item. It had the shock mounts for the rack removed because when they were installed, the stresses were even more because it ended up with a resonance that started breaking cables and the like. So I decided to try this thing without the shock mounts to dampen some of the swing, the momentum. So it's quite an interesting test, but generally you'd say that didn't fare well, it came apart. Let's discuss the 516 shock testing just a little bit. The purpose is to provide confidence that material can withstand shock events, provide data for packaging design, and test the strength of attaching devices is the more typical things we're trying to evaluate here. There's 8 procedures defined with several of those becoming functional. There's usually a functional shock associated. Also material to be packaged, fragility, how sensitive are things, transient drop, a crash hazard test, bench handling, pendulum impact, something hitting the unit, and the catapult launch or arrested landing things where we end up with a very slow event with a lot of stresses involved. Shock pulses have an amplitude, usually related to some gravitational acceleration like a 10G, 20G, 30G, some function of the G-forces associated with gravity. They range from extreme to minor, and the extremes could see 30,000 Gs, but usually the duration is an extremely short event. The duration typically is a minimum continuous time that contains the RMS amplitudes exceeding 10% of the peak amplitude shown in the shock. So basically it develops an overall waveform event with a rise and fall. The shape is life cycle defined, but in general there's a couple of shapes that see more than anything else. You'll see them on the right side, and that's a sawtooth, a terminal sawtooth waveform, and a rectangular waveform or a trapezoid. The measured time gets summarized and develops how long these things happen. You also have a shock response spectrum estimates for the complex transient. So the idea is to create a waveform that has the SRS data. The classic waveforms, the terminal sawtooth for procedures 1 and 5, are more commonly dealt with. If you do have SRS data or the frequency, you're trying to simulate the ASD for procedure 1. So you could do a vibration equivalent or the applied spectral density. So you're trying to simulate through the shock an applied spectral density. That comes into the table 1 in the standard where you have 15 to 23 millisecond duration as the common event. And then you have the unknown, I don't have the knowledge for the SRS, so I end up doing a terminal peak sawtooth for the procedure based on an 11 millisecond transient or the table 2. It's a more common method. There's also the trapezoid associated with procedures 2 and 3, and we don't have a good trapezoid associated or a good waveform associated with the transient drop or procedure 4. A lot of people try to simulate this because they know the transient drop on an unpackaged device is going to cause some damage. If you drop any item from a meter or so and let it land on a solid concrete floor or some other equivalent, you end up with physical damage to the product, bends and scrapes. Now, it may survive the test and function, but it may not look so pretty afterwards. You may have some bent connectors, handles, things of that nature. It may prove to be a failure, but it may prove just physical damage to an expensive test article that we're trying to continue to keep our efforts going to make it useful for other things. So the transient drop, quite honestly, gets another waveform applied. You need to have some sort of information from a mass equivalent to figure out what waveform would be appropriate to define that. Most people I see spec out the trapezoid waveform for this event, and most people accept it as being a way to check it without the physical damage. Again, it requires coordination between the user, the customers, and those people accepting the data. The quantity of pulses are based on the potential exposure. If I'm seeing something where the shock transient happens frequently, the test may pull 3,000 or 4,000 shocks. Typically, we're looking to see if it falls apart from the random once in a while things, so 1 to 3 shocks is more typical in each direction and each axis. So we're trying to simulate these events. Again, we need to consider what the test is doing. If it's a package test, what's the mounting? Are we trying to simulate the mounting, or is it just what's happening inside? Is it a transport thing? Is it a functional thing? So we need to consider how we configure it depending on the target here. A lot of tests end up with 3 or 4 different shock configurations depending on the product and its stage in the development. You need to consider the installation. Is the item mounted on shock mounts? Is it a hard mount on a shock-mounted support? For instance, a rack equipment that is supported by shock mounts. What kind of stands or attachments are involved? Does it have support brackets? How is it mounted? What about cables? A single cable does not represent 25 cables in the forces that are applied based on the cable attachments and their weight and mass and how they stress the article during the event. You also need to consider something about the electromagnetic compatibility with the shaker. If I'm using a shaker, an electrodynamic shaker, to produce the shock pulse, the field associated with all that current flowing, the magnetic field from the shaker, may affect the answers, may affect the way the unit is performing and showing its monitoring. So if it's not compatible with the table, you need to provide some sort of isolation there, and it's very difficult to get to at times. So if you consider it, you might be able to do something about it. The test fixtures. The fixtures should simulate the installation. So many times people don't prepare fixtures. It should transfer the distributed energy to the test article, the EUT, equipment under test. Let's think about this for a moment. If I've got an item that's mounted with 4 screws to an attaching side plate, testing this item mounted directly to the table does not transfer the energy to the side plate or the mounting hardware. So we end up with a different waveform to items inside the unit than we intended because the transfer of energy doesn't simulate the real installation. We need to provide these standard attachments, those things that make it fit the way we intended it to be installed. The fixtures should not alter or produce resonances or responses on their own. So we need to look at the fixture as being an absolutely critical element to simulating what happens to the box. Now, quite frankly, a lot of boxes have so many applications, the manufacturer simply says, I need to find out what goes on inside of the worst case event, and he considers worst case to be a rigid mount with the energy hitting the unit altogether. If it doesn't fare well, then he may over-design to compensate for that. Common hardware mounting is typically called out, where we end up with a clamping mechanism, something to attach the unit very rigidly to the table so the energy is transferred from the shaker table to the unit with the energy distributed along the whole mounting surface. A lot of people consider that worst case, and it could be true because it takes the impact of the shock, the short transient, and maximizes how much energy is distributed into there. However, it may not be worst case on attaching points that need to be evaluated. Does this thing come loose in the real world? Does the attaching points stay attached? And a clamp or common hardware method does not make worst case of that kind of evaluation. And what attachments are replicated? Well, if I end up with a clamping mechanism to actually install it wherever it's going, then it does represent something. But in general, we're not doing something without a fixture. Does it properly transfer the energy to the internal mounts or components? Well, it takes some analysis to figure that part out. So we need to really considering we need to do this. It has a place, but it needs to be depending on how the controls or those methods that we use for feedback to determine what energy got sent to the unit. So depending on how we control or monitor the events, we may be able to get a very good test or a very bad test. For the vibration control, the feedback that measures and controls the input spectra to produce the profile. Well, should this thing be based on the vibration characteristics installed? It should be based on the vibration characteristics in the installation. For an acceleration input, it's based on the planned for input to the unit, to the material. So we end up attaching this item and look at the acceleration at the point of impact. In other words, place our monitoring system with the unit but not on the unit. We're applying something and says the unit will react based on what we applied. There's a force control method where we end up placing force gauges as a feedback, so the feel for the measured forces. Again, you need a lot of life cycle data to determine if this is the proper way. There's an acceleration limit where distributed monitoring happens with the EUT with established limits. Something's happening on the EUT and you say, well, don't let it go beyond that point. It's part of the vibration profile. So it kind of compensates for an improper mounting saying, well, we're going to control the input to produce this output. And there's an acceleration response, a control based on monitoring at an EUT test point. Not something where we have a lot of points on the EUT, but a central control to say, well, I want to get this much G-force at the circuit board. So we may put an accelerometer or a measurement system inside the box at a particular point. The tolerances on this are pretty well defined. With acceleration spectral density, the ASD, generally is 3 dB, and it varies more with large test items, but you need a good measurement system to attain this with a lot of spectral degrees of freedom. Typically they ask for more than 120, so you get a lot of allowances here to get and what's a good measurement system. The peak sign acceleration could be a vibration that maintains tight control with a good measure of the peak versus RMS. And remember, the RMS is 0.707 times the peak. So we're looking at peak versus an RMS. Consider that in defining the numbers. The frequency, the system asks for a 1.25% frequency accuracy. So if you're doing 50 hertz, it expects to be doing 50 hertz. An ignored piece of information, the cross-axis acceleration. If you're doing a vertical acceleration, what's happening horizontal, left to right, the transverse or longitudinal axes? These should be monitored and try to control them. If I'm getting a lot of cross-axis acceleration during this vibe test, something is typically wrong with a resonance or a fixture. It could be the unit, but we need to look into this to see if we're addressing a bigger problem. Do we have a loose mounting fixture? Is something going wrong that allows a resonant in other directions which may cancel or multiply the effects of what we're actually doing? So consider monitoring cross-axis acceleration as a typical place. We need to examine this, and quite frankly, I seldom see that at most places that we set up tests, including our own. The shock controls. The method called out in the standard calls for a calibrated measurement device, an accelerometer typically. a calibrated load with the mass of the unit and the stiffness of the unit. You need to produce 2 consecutive applications, measure the response from the load, and you verify it conforms with the test tolerance. Well, that's great, but nobody does it. Well, excuse me, I can't say nobody. Very critical systems may do that. But in general, we subject a unit to this, and if it breaks, we put another test article on in its place. If we've overdone it in getting the definitions clearly defined. So the reality is we seldom go to this trouble. It requires building a test fixture and a mock-up of the unit so we can damage it without damaging the actual test article. See how it's going to calibrate everything and then apply the calibrated things once we put the EUT in place of the simulator. It would be an ideal world if we could do that, but the time and planning are excessive for most things that need to go into the lab right away. Another poll question, Belinda.
Thanks, Steve. Third poll question. The EUT is an item in a shock-mounted rack with a rear support. Which configuration below is appropriate for vibration and shock testing? We'll give you a few seconds to answer the question. We need a few more votes. Okay, we have some coming in. And results are about 34% said rigid attachment to fixture, and 34% a tie installed in a shock-mounted rack. Back to you, Steve.
Well, obviously installing a shock-mounted rack, the actual one that you're going to put it in, is an ideal situation. You get all the movement of the rack. You are able to test the mounting structures, the rear support bracket and how it affects things, and the cables installed in the rack versus hanging out someplace, and any support structure you get there. Remember, this thing should be fully equipped. It should have the full cable assemblies, all the things going on to simulate what is really happening. So installing a shock-mounted rack is ideal. Most times we don't know where it's going to be placed in the rack. Is it going to be at the top, the bottom? How many other things are there? What kind of weight distribution from other components shared in the rack cause the shock mounts off the rack to react properly? So most people end up with a test item where they're trying to qualify their own piece. So they need to build a fixture that would simulate a rack mount and shock mount it accordingly. Now, if I've got a 400-pound rack and I've got a 20-pound equipment, I would have to adjust the shock mount structure. So I'm not supporting 400 pounds with the shock mounts, I'm supporting the 20 pounds. So let's consider the adjustment to the shock mounts to consider weight and mass distribution. So there's no hard fixed rule, but in general, rigid attachment of the fixture with the fixture shock mounted seems to be a way to go in lieu of the shock mounted rack. Okay, hopefully everybody needs to do that. If not, you can send me some questions about it. Let's look at the test duration associated with this item. The life cycle plan should define what's going on with the test durations. There's vibration guidance in the international ITOP. I can't remember what the TOP stands for. Test Operating Procedures 1-2-601. And by the way, they don't include fixed-wing aircraft as part of that. But they talk about the shocks determined by, that's vibration guidance. Shocks are usually the quantities determined by the exposure and how much information you have or don't have, what kind of waveforms, etc. Decisions are frequently based on the type of test, if it's development, qualification, functional, or durability. In the overall sequence, dynamic tests, vibration, shock, etc., may influence other conditions, temperature, altitude, humidity, leakage, and EMC, because now if I've developed a crack in my shield or shielding effectiveness destroyed, I may have to consider those elements. Climatic tests, temperature and altitude, may influence vibration and shock. So we need to consider which ones are first. Generally, vibration and shock are early in the test sequence. The use of multiple samples generally is not a good practice because there's no evaluation of the combined effects is accomplished. Many of us have seen frequently the fact is one test article comes to the environmental world, another test article goes to the EMC world. Nothing contributes into this, and we just included EMC in the game, which is seldom evaluated. We talked about that as dynamic tests affecting EMC. Let's consider a test item and just talk about the design for just a moment. I have a unit being built and it's placed in a plastic container, some sort of enclosure that has some conduit mounts attached or some cable entry points. And because of EMC requirements, they decided to use a spray applied coating, some sort of a coating material that's usually a paint with a conductive material to provide shielding. Well, now, I don't know how many of you have ever dealt with that kind of product, but let us consider placing that item in a temperature chamber and allowing it to cycle hot and cold for 3 days. And then we bring it over the vibration table and shake it for about an hour. And if you open the box up, you can pour little flakes of copper or gold or whatever out of the box. Well, when I'm removing that coating material, I'm removing the shielding that is so critical for EMC performance. So failure to do this test in that sequence may or may not identify the true problem. So we've got a lot of interactions above just the fact of the shaking might cause a crack that allows water to get in during immersion or some ingress test. We've got other influences here that seldom go through the cycle. So the product design needs to be fully evaluated and brought forth. Now, here's the difficulty. A lot of test programs aren't defined at all. They come to the test lab, do these things. The test lab is considered to be the place to get the information. The test lab seldom knows the product design, intimately enough to develop a good program, especially since a lot of this is happening so early into the test game that we don't have a chance to capture data. So the idea is that we need to develop a good program. It can't happen at the last minute. It shows up at the environmental lab and planning then starts because it delays everything in getting the approval. Let's consider the whole thing. The users need to be brought up into this manner so they can understand what they're trying to accomplish, or they need to at least be able to tell you what you're trying to accomplish. Because quite frankly, these test programs don't always clearly understand that. A test interruption. There's about 3 things that cause an interruption. The lab equipment malfunctions. So if that's the case, we need to examine the data to see if there was an overtest as part of it. If there's no overtest, you resume the test at the point of interruption. If there is an overtest, analyze and determine how we go forward with the program personnel, the engineering staff associated with the product. If the test item fails, generally they say replace the article and start again. An alternative is to repair, replace non-functioning components and restart. For instance, a circuit board damaged and continue from there. It may overstress the remaining pieces because they're getting a longer duration exposure because we restarted the test at the beginning. Expensive and unique test systems, you need to analyze and determine the path forward. I've got one-of-a-kind item that's going through the testing. We need to figure out how it affects things. And scheduled event interruptions. For instance, there may be things associated with scheduled things, like restrained cargo, where the restraint straps get tightened at frequent intervals. The vehicle stops and then you're able to adjust and recalibrate. Scheduled maintenance events may be something. So we make that part of the scheduled event and make it part of the test program with the scheduled event well defined. We need to have the test acceptance, the function. When there's operational checks to be made, what's the pass-fail criteria? Do we need to do a complete acceptance test procedure? Measurement functions. Turning something on and see that the fan starts is not necessarily saying that the unit doing measurement functions gives us the right measurements? Did we lose calibration on integral sensors? The mechanical inspection needs to happen. Broken glass, plastic, structural cracks, frame cracks, chassis cracks, loose parts, connectors not being attached right anymore, binding and jamming of doors and windows and things of this nature where you can't access the things you need. And you need to see if you influence subsequent tests when you're doing this evaluation. And did the subsequent tests cause this not to be evaluated properly? Another poll question, Belinda.
Okay, how do we determine the test duration? MIL Standard 810G specifies the duration for each test. Test procedure defines the duration, life cycle analysis, or deployment locations. We'll give you a few seconds to answer the question. I'm getting a lot of responses in. A few more seconds. And the majority went with life cycle analysis.
Well, everybody's been listening, because that's what it says we need to do. The life cycle needs to determine what we're doing. They refer to the ITOP as having some guidance if we're not quite clear on that. MIL Standard 810 seldom gives you any duration items, and the test procedure may be an option because we don't have a life cycle. So somebody writes a procedure and say we're going to do it this duration and justifies why and gets general acceptance. But the life cycle is clearly the place we need to be at. What is defined for this product? We need to consider tailoring as part of an overall evaluation program. It's based on common sense considerations for material and its applications. The details of the evaluation process and the methods are involved in, and test method details involve the tailoring. When do we combine tests? For example, we may choose to do the method 520, the temperature, humidity, vibration, and altitude. There may be special conditions and life cycle or scheduled events that are considered part of the tailoring. We need to plan for vibration and shock. It's an essential part of it. There's a lead time to properly get a test fixture and evaluate where we're trying to be. It provides details on the methods, controls, and procedures. And above all, it gets everybody on the same page. This is how we're going to evaluate the details of the evaluation, and everybody signs up to that agreement. So the questions get answered before they become questions. The problem may be, how do you get your tailoring accepted? A common sense approach sometimes can be misread as trying to get out of something. So it's a matter of people trusting. The idea is I'm not trying to escape it, I'm trying to make sense of this. So if we have a good interaction with the ultimate user, the approval of the systems, these systems work much better together with getting the approval of a tailored program that makes sense for the application. The test procedures are derived from the life cycle environmental profile. But as I've said previously, why does it become such an elusive document? Well, there's a lot of efforts to be made into COTS programs. Products are deployed everywhere, so worst case is often stated until the totals start appealing. You test forever and a lot of money involved. An agreement needs to be made and documented. This is the procedure. It details the tests, the durations, the sequences, the levels, the configurations, any special considerations. For example, if you're doing fluid contamination, which fluids? If you're doing shocks, how many shocks? The user and the manufacturer have a clear scope defined, and the test lab knows the obligations and how to execute the program. It's not into a constant, should I do this before that one? Should I do this? What test method and procedure and level applies to X? The procedure should have the escape clauses. What happens if? You need to look at these things that happen. Like what happens if I get a random failure that I cannot duplicate? How many times do I got to look at this thing before I say, well, it's just a rare event, it's not real? If I have an item that checked out at the end of a test but failed to start the next day for the next test, how do I handle that situation? Any deviations? I come up on a problem during the test and saying, okay, now what do I need to do to compensate for this problem? Amount didn't get clearly defined. Something comes loose. How are they processed? Who signs them off? Who accepts them? So we need to have that defined in a procedure. You should do that every time. The acceptance criteria should be clearly defined. You know, that pass-fail, got to know what's acceptable. Should be measurable, have an objective value, a tolerance, something other than plus or minus 0. That's not realistic. Some quantitative value. And if it can't be quantified properly, a subjective issues need identification of who will make the decision. Is it the lab manager, the test technician, the person monitoring the activity? The customer says that's acceptable or not. That needs to be really clearly defined. The supporting monitoring equipment associated with the job should not be subject to the test. You shouldn't put a piece of monitoring equipment inside the cold chamber or on the shaker table, and it should not influence the results. If this thing is exposed to how much influence its design may need to be every bit as good as the item itself. So figure out how to isolate the support monitoring equipment and make them non-characteristic of the acceptance. A lot of other standards come into play other than MIL Standard 810. The IEC 60068 series has a lot of environmental tests. DO-160 for commercial aircraft. They have a lot of special applications for commercial shipping, power production, space, but they all have this common theme: tailoring and life cycle considerations. We need to bring those into being at all times. And with that, Belinda, I went through the presentation. Do you have any questions at this point?
Okay, thanks, Steve. We would like to have a call for final questions from our audience. Please enter any last questions you may have in the navigation pane. We have received quite a few inquiries on where to get additional information on this topic. There's a vast amount of content found on our website, www.environmentaltestanddesign.com. You can also email us at info@etdnews.com with specific needs, and we can direct you accordingly. Steve, here's a question that we received. Why isn't the half sign listed as one of the classical shock pulses in your presentation?
Well, the half sine wave used to be one of the more common classical shock pulses a few years back. It came into not a normal classical shock because it doesn't represent the spectrum, the amount of waveforms, because at one time it was considered that only the pulses that represented 50% of the total spectrum got considered, and now it's been brought forth to 10%. So what that did was it created a different spectral content view and removed the half sign as being a prevalent. Now, don't get it wrong, half sign is still a pretty typical waveform, and it has its applications, and it can be used if there's something that says that would be what would be expected. For instance, a drop shock sometimes is considered a half sign program. So, and the duration. So don't consider it as not being classical. It's just not one of the accepted standards. But there are reasons to do this. But it usually involves having some information about the waveform and how it's being affected. Quite frankly, if I were doing a drop shock simulation, I would probably go with a half sign because you can get a large variety of durations. So, but the trapezoid tends to be more commonly accepted. But don't throw it out. It's still around and can be brought into being. Anything else?
Okay. Do you ever have things really prepared properly for testing when it arrives, meaning well-defined procedures and fixtures?
Yes, I do. There's a lot of high visibility customers that have expensive articles. NASA, for instance, they don't get many opportunities to get it wrong, because when you're dealing with equipment of their nature, it's one of a kind or very few, and so they must absolutely have a good program defined. A lot of other customers with similar requirements tend to be more clear about defining their product, because there's no recovery point. Once it fails, it's a disaster to the whole program, not just a little bit. So they tend to invest more into this development and designing the test. So yes, we do get them frequently, but not near as much as I'd like to see.
Okay, and one more. Are there specific tests that really need to be accomplished only after vibration and shock?
There are several that are defined. They say shock and vibe early in the program, and that's usually the case. I would say that that's clearly things for ingress needs to happen after these things. If I've got a rain or an immersion test, doing that before shock and vibe makes absolutely no sense whatsoever, because that's where the openings and fractures and cracks will appear and allow things to be clearly defined. Remember, during those tests, you need to have any way to evaluate and see that it's in good shape prior to doing those tests. So sometimes a lot of people look at ingress before and after a dynamic test. Usually it's an overkill, because at the end is where the answer has to be performing. After I've shocked it, transported to the site, it needs to be immune to the effects of the ingress when it's in actual use. Okay. Anything else?
I think that's about it. If anybody else has any more questions, definitely send them to us. We have received so many great questions we will try to address in the future. Steve, thank you again for your time and expertise. Webinar attendees, if you have any more questions we didn't answer here, please send us an email at info@etdnews.com. A recording of this webinar will be available on our website, environmentaltestanddesign.com, shortly. We will also send a link to all participants. Thank you for attending.